Welcome. In this video, we're going to introduce drawing Lewis dot diagrams for a molecule. And in your textbook, this covers it in chapters 9.3 and 9.5, and also in section 9.7. So there's some of the relevant textbook sections in TRO if you're interested. So Lewis dot symbols. What we do in Lewis dot symbols is we use dots to represent valence electrons. So here's an example. We've got an atom of oxygen. If we look at its electron configuration, we see that it has 6 valence electrons. And if we were to draw the Lewis dot structure, we would draw it with 6 dots. And typically when we are drawing a Lewis dot structure for an individual atom, what we do is we put 1 dot on each side first. So we go 1, 2, 3, 4, 5, 6. That's why and you end up seeing that oxygen has 2 unpaired electrons, and that kind of fits with what's going on in the 2p subshell. It's got 1, 2, 3, 4 electrons there. Notice how it has 2 unpaired electrons. And we'll see that those unpaired electrons are typically kind of spots where you can form bonds. So there's your Lewis dot symbols. And when we're doing molecular covalent bonding, a group of atoms called a molecule, they share electrons, and we can use these Lewis structures to represent the electron sharing which occurs. So what's going on in a molecule of hydrogen is that you have 2 hydrogen atoms coming together and sharing their electrons there, like this. And Lewis structures are representations of molecules that show all the electrons both bonding and non-bonding. This is important. If someone asks you to draw a Lewis dot structure, you need to include both the bonded pairs and the non-bonding pairs. And some of the kind of guidelines that we use for this is we use dots to represent the non-bonding electrons. So like over here in this molecule of chlorine, Cl2, there are several electrons that are there but aren't involved in the bond, so we represent them using dots. And for the bonding pairs, we can either use 2 dots or 1 line. So when you're looking at a Lewis dot structure, each line represents 2 shared electrons. So just keep that in mind. So 1 line is equivalent to 2 dots, and remember the dots represent electrons. Okay. I guess let me give you another quick example too. With water, right? You may have seen H2O is drawn like this, right? This example is not a Lewis dot structure. This is something that's called a structural formula. So a structural formula just shows the bonds. A Lewis dot structure would show both the bonded and the non-bonded pairs. So just want to show you a quick comparison there. So we're going to be focusing on drawing Lewis dot structures. They show both the bonded and non-bonded pairs. All right, a reminder, the octet rule. And we will later go through that there are actually exceptions to this octet rule. But for right now, we're just going to talk about the octet rule because in general, it's a good rule that most often gets followed. But with the octet rule is that atoms tend to gain, lose, or share electrons when they're bonding until they are surrounded by 8 valence electrons. And that corresponds to having full S and P subshells. That's where that number 8 comes from, is S2P6. And in ionic bonding, atoms will get an octet by either gaining or losing electrons, right, forming ions. In covalent bonding, atoms will get an octet by sharing electrons. The main exception to this octet rule is that first row. If you're looking at like hydrogen, helium, all they have is a 1s, so they won't end up with an octet. So they'll just end up with 2 valence electrons. All right, so we're going to go over the steps to drawing a Lewis dot structure. And this is really key. You've probably learned how to draw Lewis dot structures using a different method, depending on where you took general chemistry. You may have learned it a different way. And today we're going to work on changing our frame of reference with a new technique, and this technique will help us with more challenging problems and exceptions to the octet rule. So right here I'm giving you some steps. It's important to actually follow these steps and pay attention to them. Don't just say, oh, I already know how to do this, because the way that you're doing it already might not work for you once we get to the more complicated examples. So we're going to go through what these 5 steps are. So step one is find the sum of the valence electrons of all the atoms. So what you're going to do is you're going to look at your periodic table, and here I'll flip ahead. Here's your periodic table, and you're going to find, like, we're looking at PCl3 as the example. So you're going to look at phosphorus. You're going to say, okay, it's got 5 valence electrons. And then you're going to find chlorine. You're going to say it's got 7 valence electrons. And then you're going to say I've got 3 chlorines and 1 phosphorus. So I'm just going to add those all up. And I'm going to write it down somewhere. This is important. Like, actually commit to this number and write it down somewhere. It's going to be a good way for you to come back and check your work at the end. So this is the total number of valence electrons. That means this should be the total number of dots in your picture at the end. You might end up with drawing Lewis structures of a polyatomic ion. So you might have an anion or a cation. So if I, for example, were drawing the Lewis dot structure of NO3 1 minus, I would add up the valence electrons in 1 nitrogen and 3 oxygens. So I'd add those up. It would be 5 plus 6 plus 6 plus 6. And then since it has a -1 charge, I'm going to add an extra electron there. So that's what you do if it's an anion. You're going to add an electron for each negative charge. So you might be adding 2 or 3 electrons. If it's a cation, like for example, the ammonium ion is a positive charged ion, what you do is you're going to take an electron away for each positive charge. So in this case, I would look at my nitrogen has 5 valence, and I've got 4 oxygens. So I have 4 electrons from each oxygen. And then I'm going to take away an electron from the total, because it has a positive charge. So step one, add up your valence electrons, commit to it, write that number down somewhere. Step two, figure out what atom goes in the middle. The central atom, so the one in the middle here, is going to be the least electronegative element that isn't hydrogen. So never put hydrogen in the middle. But otherwise, the central atom is going to be the least electronegative element. And how do you figure out who's least electronegative? Is you use your periodic trends, okay? We know that electronegativity increases as you go across a row and up a column. So like over here, fluorine is the most electronegative element. So if I'm looking up here, phosphorus and chlorine, chlorine's further to the right on this row, and so it's going to be the most electronegative. That means phosphorus is the least electronegative. So a good rule of thumb is put the one that's further to the left in the middle there. So I'm going to put phosphorus in the middle, the chlorines on the outside, and then I'm going to connect with single bonds. So I figure out who goes in the middle, then I connect everything with single bonds. Remember, you can use a line to represent 2 dots, or you could draw 2 dots like this. This would be the other way of doing it. Okay. And remember, 1 line or 2 dots represents a single bond, which is 2 shared electrons. And then what we want to do is we want to keep an electron tally going. So remember, we decided earlier that we have to have 26 electrons in our diagram. And then I want to say stop and count and say, how many have I used up so far? So far I've used up 2, 4, 6 electrons. That means I have 20 electrons left. And this running tally is important. All right, what we do next is we give the outer atoms an octet first. So what I did here is we just added dots to all the outer ones, the chlorines. And if you're wondering why are we doing the outer ones first, remember the outer ones are the more electronegative atoms. So they kind of want the electrons more, if you think about it. So if we have some electrons, we're going to give it to those more electronegative elements first. And then keep track of the electrons. So I've just used up 2, 4, 6, 8, 10, 12, 14, 16, 18. I just used up 18 more electrons. So I'm going to keep my running total going. And now I have 2 electrons left. So this next step, put any leftover electrons on the central atom, even if doing so results in more than an octet. This is key. We will see this later on in the week. We will see that sometimes you end up breaking the octet rule. You end up with even more than 8 electrons on the central atom, and that's okay. And that's why it's really important we kind of keep a running tally of how many electrons should be in our picture. We don't want to just assume everyone will have an octet, because our number of electrons might not work that way. So this is a key step. And then if you run out of electrons before the central atom has an octet, then try multiple bonds. So try doing a double bond or a triple bond. And those are the only two options for multiple bonds. You can have a double bond or a triple bond. There's no such thing as a quadruple bond, so we will not see that happening. So the most common mistake I see people doing is trying to form a double or triple bond when it's not needed. So notice how this is the very last step. So you only use a multiple bond is if you get to, this stage and you don't have any electrons left for the central atom and you still don't have an octet yet. So like notice right here, HCN, we only have, let's see, 10 electrons to work with in the structure, and right now we've already used up 2, 4, 6, 8, 10. All my 10 electrons have been used up. I don't have any dots left for carbon, but carbon doesn't have an octet yet, right? It only has 4 electrons around it. So in order for it to get an octet, the only way I can do that with the number of electrons I have is if I do some extra sharing. So nitrogen, instead of hogging all these electrons to itself, it can share some more of them with carbon, and that's how you end up with this structure right here. So the really key thing though is this is your very last step. Only do it if you've run out of electrons and not everyone has an octet yet. All right, so here's some practice. So I'd recommend you do is you pause the video right now and try these, and then come back and check your work in a minute. So take a moment to pause the video. All right, now you're back after trying these ones. Let's go over these. So step 1 is we're going to add up the valence electrons. So nitrogen is 5, and then I've got 3 fluorines that are each 7, so that adds up to 26 electrons here. And then I'm going to put the least electronegative element in the middle. So if I use my periodic trends here, it looks like here's nitrogen, here's fluorine. So nitrogen is the less electronegative than fluorine is, because we're thinking about this trend here. Okay, so I'm going to put nitrogen in the middle. And I'm going to connect everything with single bonds. So step 2. Step 3 is give my outer elements an octet. And then I'm going to stop and count and see how many electrons I've used up. So I had 26 electrons, and I've used up 8 plus 8 plus 8. I've used up 24 electrons. So that means I have 2 electrons left. So my next step is I'm going to put the leftover electrons on the central atom. And then I'm going to stop and check to see if everyone's following the octet rule. And it looks like we're good. Every atom has 8 electrons around it. So basically 2 good things to check for is, are you following the octet rule? And then do you have the correct number of electrons in your picture? So right now, everyone in here has an octet. And then I also have 26 dots in my picture. So that means my structure is all good. Yay. All right, let's go on to this next one. Chlorine has 7 valence electrons. And then I've got 3 oxygens that each have 8. And then I'm also going to add an extra electron because it's a negative ion. Okay, so that gives me 6 times 3 is 18 plus 8. I still have 26. Okay, same number of electrons here. Okay. And then I am going to put the least electronegative one in the middle. Chlorine and oxygen is kind of harder to tell because they're both right near fluorine. So I'll just tell you, if you look up the electronegativity values, it turns out chlorine is less electronegative than oxygen. So, whoops. So we are going to, whoops. Let me go back there. Okay. So we are going to put chlorine in the middle because it's less electronegative. And then we're going to attach the oxygens with single bonds. So step 1, count the electrons. Step 2, put the least electronegative thing in the middle. Step 3 is we give your outer atoms an octet. And then we stop and count. How much have we used up so far? Notice this is looking a lot like the structure above it. We've used up 24 electrons. We have 2 electrons left. So those last 2 electrons are going to go here in the middle. And notice everyone's got an octet, and we have the right number of electrons in our picture. So those are the 2 things we're looking for. What you might notice is this structure is probably a lot different from what you might expect, because if we just drew the individual Lewis dot structure for chlorine, we would only expect it to form 1 bond. And notice that in this polyatomic ionic, it's actually forming 3 bonds. And each of your oxygens are forming 1 bond when we might expect them to form 2 bonds. So this is one of these reasons why we're using this strategy that we are using here to draw these Lewis dot structures, because it would be hard to predict this structure just by looking at the individual, atoms structures here. So anyways, this is what happens. Might be a little weird from what we're used to. Okay, let's look at this last one, CS2. So if you look at carbon, has 4 valence electrons, and you've got 2 sulfurs, they're each 6, so that adds up to 16. And you put the least electronegative one in the middle. Again, let's look over here. Here's carbon, here's sulfur. So the one further to the left in general is going to be less electronegative. So this is, again, a kind of tricky one to figure out, but trust me, let's put carbon in the middle. And then we put sulfurs around them. We start with a single bond. Okay, and then we give the outer ones an octet. And then we stop and count and say, how many electrons have we used up? So we've used up 8 plus 8. We've used up 16 electrons. So we have no electrons left. But if we stop and look at our structure, notice carbon does not have an octet yet. So here's where we can use multiple bonds. So we need to give carbon an octet, but we've run out of electrons. So what we can do is we can have these sulfurs share some of their electrons. And so the correct structure for CS2 ends up looking like this. All right, so that's an intro to Lewis dot structures, and we will continue on with this more later in the week.